Welcome everybody to this summarized presentation of my thesis, which has a long name. This work was co-tutorized by Professors Ramon Codina and Joan Bages at UPC, Barcelona and CIMNE. So I will proceed following the structure of my thesis, following the same chapters. I will start with a brief introduction of the physics behind human voice, as well as the numerical framework of computational aeroacoustics. The following two chapters, 2 and 3, will be mainly devoted to acoustic models based on incompressible flow. Then chapter 4 will correspond to a compressible alternative. I will skip chapter 5 due to the time constraints, but you can ask anyway later on during the lunch. And finally, I will finish my presentation with the results corresponding to an LES simulation of Sibyl S aeroacoustics. So first of all, regarding the physics of human voice, we can divide this phenomenon into two main parts, mainly voiced sounds and unvoiced sounds. Perhaps the most known example of voiced sounds are vowels, and they can be simulated as the propagation of a known analytical function, which in this case are the glottal pulses. And then we are talking about characteristic frequencies, or formants. On the other hand, when we are talking about unvoiced sounds, here turbulence has an important role, because voice sounds can be produced by the impact of an air jet against one or more obstacles within the vocal tract. And then we're not talking anymore about a characteristic frequency, but a characteristic frequency spectrum. Here this example corresponds, to the fricative S that I will show later on. So when we talk about voice sounds and a sound generation due to turbulence, we have to talk about the compressible Navier-Stokes equations, which are the only ones which provide an exact solution for this problem. However, as we all know, this approach is very costly and is unaffordable in most cases of problems like this one, with large-scale problems with 3D geometries and so. The same happens with turbulence. We can proceed with a direct numerical simulation without modeling turbulence, but it's normally also unaffordable for 3D problems. Then we have to resort to an approximation, which is the large eddy simulation, which in spite of a high computational cost is feasible. On the other hand, RANS is not valid for computational acoustics. Well, as I have shown that, as I have said, that the compressible approach is not always available due to its cost. From the 50s on, hybrid methods have been developed. One of the most famous examples is Lighthill's analogy, and these kind of methods segregate the flow scales from the acoustic scales. So we solve two uncoupled problems. How do we do that? Well, in case of Lighthill's analogy, we take the compressible flow equations, we rearrange them, obtaining a second order wave equation with this source term, which corresponds to the flow noise source term, Lighthill's tensor. Once we have obtained that, we can apply the incompressible flow approximation at a source term level, and then we can compute our sound propagation with incompressible flow solver. However, we have several disadvantages with that. In a certain way, we are not separating flow and acoustic oscillations. Here we account for the full pressure oscillations. We only account for propagation in uniform flows because we are sending our advective operator to the right-hand side. And we are also neglecting the acoustic feedback on the flow scales because, in fact, we are segregating both of them. Then, to summarize, our computational framework, as I have just said, is based on computational acoustics, the finite element method, and the variational multiscale method, which we use to stabilize our flow equations and also to provide the turbulence modeling for the LES. We use our multiphysics FEM code, FEMUS, and we have adapted it to high-performance computing. I will show this later on. The objectives of the thesis are then, first of all, getting rid of the human voice topic. First of all, developing computational aeroacoustic tools which can be used at any engineering problem, and also integrating them in high-performance computing environments. And finally, applying them as well from both incompressible and compressible approaches to the problem of human phonation. Well, then let me start with the first formulation of my thesis. This is the concurrent finite element simulation of quadrupolar and dipolar flow noise. And the motivation behind this formulation is that, as I have just said, Lighthill's analogy does not assess the contribution of solid boundaries or solid bodies in the generation of sound, because it's only valid for free field propagation. We can use, for instance, green functions, but green functions are only available for very simple geometries, which is not the case of a realistic vocal tract. And on the other hand, we can also use as an alternative Curl's analogy, another hybrid method, which identifies the rigid body contribution to the sound generation with a dipolar distribution source term, which is this one. But this has also a problem. Here we find that we depend on the full compressible pressure, which is not available in an incompressible solver. So we have to find a solution in order to adapt this method to incompressible flow solvers. How do we do that? Well, very easy. We associate this surface integral, this source term, to the body diffraction of turbulent noise. What does it mean? Well, first we solve, as expected, our incompressible Navier-Stokes equations, and once we have extracted our source term, we go to the wave equation, Lighthill's analogy, and we decompose the problem in two components: an incident problem and a diffracted problem. As you see, the incident problem will be solved in the whole domain without any object in the free field, but with the source term generated by the flow. On the other hand, the diffracted problem will be a homogeneous wave equation solved in the realistic domain with the object in it. And in order to guarantee that the summation of these two problems gives the original one, we have here a boundary condition. Results. Well, if we go to the Aeolian tones case, a very typical benchmark, we see how the propagation, the total acoustic propagation, or total acoustic pressure looks like. And then we decompose it in two components. First, the incident component, which captures most of the flow scales which do not propagate. We must take into account that this scale here is 5 times smaller than this here, which is the diffracted one. And the diffracted component, the dipolar component of sound, shows us that is the biggest contributor to the radiation at the far field. This was already calculated and shown by analytical models, but now we have proved that, well, we show that in a finite element code. This will be very interesting in the last chapter because we will be able, with this composition, to show what's the contribution or in which extent the importance of upper incisors is the best contributor to the generation of the fricative sound S. However, in spite of this trick, of this decomposition, we still lack some features because Lighthill analogy has some restrictions, as I have said. For instance, the fact that it's only valid for uniform flows, or free fields, and it does not filter the scales. So the oscillations that we see include both flow oscillations which do not propagate and acoustic propagation to the far field. How can we solve that? Well, with the second formulation I'm going to present now, I will present it briefly. It's quite large chapter of my thesis, but I will go through quite fast. These are the acoustic perturbation equations, which we have stabilized using finite elements. So these acoustic perturbation equations, they provide a wave propagation which is also valid for non-uniform mean flows and performs a complete filtering of the acoustic scales. How do we do that? Well, we depart from the linearized Euler equations and we decomposed all variables u, p, and ρ into two components, an incompressible one and an irrotational one, which corresponds to the acoustic field. Then we perform, not at the source level, but at a problem level, the incompressible flow approximation, expressing ρ in terms of p. And then we obtain this set of two equations depending only in acoustic pressure and acoustic velocity. As you can see, stabilizing this is quite a nightmare. We have done that. The implementation is also quite harsh. And yeah, the computational cost, you can imagine, is much higher than the previous approach. However, the results are quite interesting, though. You see here the original Aeolian tones problem, and here the one computed with the acoustic perturbation equations. Here you can see how the influence of the advection of the flow is transferred also to the wave propagation, which is advected downstream, unlike this one. However, as I have just said, some drawbacks have been introduced with this formulation, implementation costs, and also computational cost. So we asked ourselves if we could think about a method that is valid for any geometry, that accounts for the effect of turbulence on the wave propagation and refraction, that accounts for two-way coupling, so no segregation, that considers acoustic feedback to the flow scales, and that can be accurate not only for incompressible flows or low Mach flows, but also for a wide range of subsonic flows. And we took the decision to work with an intermediate approach, neither incompressible nor fully compressible. And this is the isentropic approximation, which is realistic in many aeroacoustic problems which do not have shocks or any thermal coupling. What do we obtain with that? What do we gain? Well, easy. A single rank calculation with only two variables, and a better conditioning than incompressible or incompressible solvers. Let's take a look at that. Well, I will go through that quite fast because it's not new at all. This is the derivation of the isentropic compressible equations for an ideal gas, taking the profit from the thermodynamic relations of an ideal gas. We can obtain this set of two equations where we still have density, variable density, and variable c, sound speed, in the equations. We will condensate this later on. I will show you how. But in fact, this is not new. The novelty of the method lays on this boundary term here. After deriving the YIC formulation and iterating by parts, we obtain this boundary term, which has a certain particularity. This one, that this is, as I have just said, a unified solver. So we need to design, to implement boundary conditions that are compatible for both flow and acoustic scales. Otherwise, our solution would be polluted by the waves bouncing back to our domain. Well, I also said that we are only using two variables, u and p. However, in this boundary conditions black box, we allow ourselves to decompose u and p into components, a mean flow component that we design like that, and a purely acoustic component. And then we prescribe separate boundary conditions for both components at the same time. So we have the first kind of boundaries we have is gamma S, which is Strong-Dirichlet. This doesn't change anything because it will not be included in our YIC formulation. And then we have gamma L and gamma O. Gamma L corresponds to all that boundaries where the mean flow is prescribed a certain value with the Dirichlet boundary condition, and where the acoustic component at the same time must be prescribed a non-radiating boundary condition, for instance, Sommerfeld. Gamma O is the outlet. Here we have traction 0 for the mean flow, and also a non-radiating boundary condition for the acoustics. Then we decomposed this boundary term. In red, the terms corresponding to gamma L, in blue, those to gamma O. But there's still something to do. We need to prescribe mean flow, a Dirichlet boundary condition for the mean flow, for the truncation, and also, of course, for the inlet. How do we do that? With applying Nietzsche's method. Why? Because if you prescribe strong Dirichlet boundary conditions on this boundary, the waves will not be able to abandon the domain. So we must keep this boundary transparent and compatible with the waves. So we discretize these boundary conditions in this manner, and then we also express our mean flow variables and our acoustic variables in terms of the full variables, like this. So we again have a solver which only sees two fields, total U and total P. Then we linearize our equations. I will not show the full equations because that's 2 slides. And then we condensate both the primitive density and the primitive sound speed. How? Taking profit of the thermodynamic relations of an ideal gas. and we express them in terms of velocity. So finally, we have this bilinear form only in terms of u and p. The results. Well, if we take also another famous benchmark, the Reynolds 1000 cylinder, we see how this approach provides the same vortex shedding, and also, and most important thing, is the decrease we obtain of computational cost. We said compared to the incompressible solver, we would go much faster, and also in comparison to the fully compressible solver, which did not converge using the same solver. Then let me show you a video where you will be able to see how this prescription, this separate prescription of boundary conditions, allows us to prescribe the flow a certain velocity on our boundaries, and meanwhile, waves are allowed to escape without segregating any scale. Can I go forward? Yes. But we are talking about an isentropic flow solver. Therefore, we thought about using this solver also for other cases, not only incompressible ones or low Mach ones. And we applied the same to a 2D flow past an open cavity, Mach 0.7. And we could represent that phenomena quite well as well. So finally, we present the results corresponding to the fricative sound. Let me show first the geometry we have used. It's a realistic vocal tract obtained with an MRI. We have refined here where the sound generation takes place, and then obtaining 45 million elements. We have computed that with more than 200 processors. And here, let me show you the results. You see how the variational multiscale method is able to reproduce the physical pattern of isotropic turbulence. So this is a success of the method. And then let me show you a glimpse of the complexity of the problem and the huge amount of flow scales that take part in the generation of this sound. You can see it here. This translated to the acoustics, we see how we are able to reproduce the same pattern of the experimental data. And meanwhile, we see how the contribution of the upper incisors in green is the dominant source for sound generation, for fricative sound generation, here, in front of the flow. Finally, this is how an S looks like in a video. And this is the wave propagation, first the initial transient. And here we see how the wave propagation of the fricative sound S looks like on a video. Well, thank you very much for your attention.